1 v1 plus mu 2 alpha 2 v2 plus mu n alpha n nu n. Same for second order. You can write mu 1 2 alpha 1 nu 1 plus mu 2 2 alpha 2 nu 2 plus mu n 2 alpha n nu n. And if you just do for higher orders, you will see that these terms are decaying because if k goes to infinity, because this is less than 1, so this one goes to 0, so it decays. And so alpha 1 v1 plus mu 2 k alpha 2 v2 plus mu n k alpha n vn. So the top eigenvalue is mu 1 is equal to 1, and the corresponding eigenvectors is 1 over square root of n, and so the rest of eigenvalues are strictly less than 1. So as I said, when k goes to infinity, the terms are decreasing and eventually converges to equilibrium. And this is exactly heat that is uniformly distributed. So you see, after a while, the heat is uniformly distributed and all the terms vanishes, and so you have a uniform heat. But mu 2, the second eigenvalue, mu 2, if mu 2 is close to 1, very, very close to 1, then it takes a lot of time to diffuse that heat. So in some directions, V2 has hard time to converge to equilibrium. So I always say it like this. It is going down, and then so if your eigenvalues, it suddenly drops. It's like that you have cluster points. Your data points, for example, is distributed like this. And of course, there are some connections, but few of them. And when you say that your mu2 is very close to 1, it means that your heat is trapped. It goes here, goes very rarely goes here. So most of the time, it's in this cluster. So it's in a very dense and hot place. So it cannot be distributed to other unknown places like this, because the probability of moving from this cluster to this cluster is very low. And so this means when mu2 is very close to 1, this means that you have sparse connections. It's very interesting, You see how physics and mathematics are related. Because now an eigenvalue can tell you what is happening in physics. And of course, the theory of random matrices is all about how you use it in quantum physics. The distribution of energy levels, quantum levels, and you represent it by random matrices and its eigenvalues. So let's talk about expansion of set. Expansion of a set. So we have phi of S is equal to this is the number of edges crossing the cut, and the volume. This is the volume of S. if you have some points, some nodes, and this is S, and you have some other nodes in your graph, and these are related to each other, but they're also related to this. For example, using these two blue edges. So you have G is equal to V and E, and all of these are G. So you want to see the expansion of the set. I mean, how much a bottleneck a set is. You remember, it was a bottleneck that didn't allow heat to be distributed, and so it's the measure of how much a bottleneck a set is. And phi star of G is a minimum of phi of S, and S is less than N2. Volume of S is less than N2. So intuition and motivation of that could be you have a complex network, biology in Facebook, in citation networks, many networks. You want to decouple billion by billion images. Your data set, I mean, not just image processing. You could use for NLP as well. You could use your financial assets as well. So you decouple it. Even you can decouple A. So it's like a fractal on matrices. You decouple more, and then you could decouple more, and then so it's like a fractal. And so understanding this allows you to know how to decouple that. Of course, using eigenvalues is the hardware. I will tell you a better, more natural way, which is very advanced, based on work of Hungarian mathematicians, which he got Nobel Prize in 2010, and I will talk about his theory and why it is so natural, because it relates probability theory to graph theory, and then you can use it in machine learning as well. So the Laplacian matrix L is equal to I minus W, and if you arrange your eigenvalues, lambda 1, lambda 2, up to lambda n, now it's just you reverse it, 1 minus mu 2. Now the eigenvalues are almost the same, so it is just reversed. And the point I want to make is that it discrete Cheeger inequality is lambda 2 over 2. So it is sandwiches, this phi star G is sandwiched between the second eigenvalue. This is really interesting. The second eigenvalue plays a major role. So the major obstruction to equilibrium are bottlenecks. So if lambda 2 is small, if this is a small, so this one is a small. And this is the intuition behind it. And, in 1979, concept of cover time. Cover time of a graph is the first time at which the random walk has visited every node at least once. And it's work by Ding Perez in 2011. And somebody has proved that n times I from n gi lambda I Vi. This is the cover time. This is the cover time of G. I mean, J in 2014 has proved that. So the next peak of this Gaussian random field is the cover time of graph. So we can but can we compute these spectral objects fast? You know, Lx is equal to B. I'm talking about different things. So, you know, it is well known in PDE theory, partial differential equations, that whenever you discretize it, you know, I had to use it in aerospace engineering, solving fluid mechanics, all of these. You know, we use advanced preconditioners in order to solve these linear equations. After, of course, you did something with either finite volume or finite difference or lots of different methods. But finally, you have to, by the end of the day, you have to discretize this and solve this. And it is related to max flows, mean cuts, and many of those problems. And because most of the entries are sparse, you are very lucky, you can use very good methods. For example, if you're interested in spectral sparsification, you can watch the videos of Spielman. His lectures on, you can watch it in YouTube. And he's a mathematician, I mean, together with other researchers. In 2010, you can learn about how they use spectral sparsification of graphs. So in the next lecture, I start reviewing not a complete survey of semi-supervised, because it is more than 500 articles. So I just review major articles on semi-supervised learning. Those articles which are cited very much and are influential, and many researchers they have many influences on many researchers, and I just want to review different ideas, because sometimes some of these ideas could be merged, and you could write another article, probably better results than the previous works. But I try to, for example, classify these the survey that I want to talk into graph regularization and graph embedding. And also I will talk about I mean, in a different setting, as either transductive or inductive. And of course, I will start by the work of label propagation of Jubin Rahmani in 2002, because it was one of the first motivation, and he is one of the pioneers in semi-supervised learning in Cambridge University. All right.